Today's episode is about converting battery storage in an off-grid home from lead to lithium. But first, please like and subscribe. They tell me it's important, but it would be really cool if you bought a copy of the Homeowner's Energy Handbook. There's a link below. And if you do get one, you'll learn tons about solar, wind, biodiesel, biogas, even making and using wood gas. Okay. Lead acid batteries work great. I've lived off-grid for about 30 years and I haven't used anything except lead. Primarily because they're accessible, they're affordable, and that's what everybody uses. But lead acid is technology that's over 100 years old, and there's nothing wrong with that, but they're heavy, they're smelly, they're filled with corrosive acid that burns when it's spilled, and it outgasses when they're being charged. And of course, the gases produced by lead acid need to be removed from indoors and vented outside. Plus, they don't last as long as lithium, and they require frequent maintenance like watering and making sure that the cables and connections remain corrosion-free. Lithium batteries have none of those problems, but they do have drawbacks. Two of the most important considerations are cost and safety. Lithium costs far more than lead, and they behave quite differently, meaning that the equipment that you have may not be compatible with the different voltages and charge profile that lithium requires. It's important to remember that there are different kinds of lithium battery technologies. In this video, I'll be speaking specifically about lithium ion. I wrote an article for Mother Earth News last year about using lithium iron phosphate batteries, which are a bit more forgiving than lithium ion. And it's worth a read if you're considering any kind of lithium battery. And there's a link to that article in the description below. So the details of getting the charge profile exactly right are extremely important. Upfront cost is a small piece of the picture. Lifetime cost of ownership is what you really want to know. For this project, I bought 4 lithium-ion batteries from 057 Technology. They were salvaged from a Tesla Model S, and because they were used, they were less expensive than new lithium batteries. In fact, they were cost competitive with brand new high-end lead-acid batteries, such as the Solar One. These lithium modules store about 5 kilowatt hours of energy and weigh about 60 pounds. These antique boat anchors weigh about 115 pounds and store about 2 kilowatt hours of energy. I'll agree that weight is not super important when it comes to off-grid. Usually the batteries are in the basement or maybe outside in an insulated shed. But size and space are an issue. Moving these things around when you have to replace them is an issue. These were retrofitted into a fairly conventional off-grid power system using outback inverters and charge controllers. The lithium battery charge profile was pretty much at the outer limits of that equipment, but newer equipment is far more flexible. I built a rack for the batteries out of some salvaged aluminum PV rail. The tabs on the batteries fit nicely into the slots on the rail, making for a pretty nice slide-in, slide-out scenario. The most important thing to remember about lithium is that it can be like a bad dog at the party. Lithium will eat the electrons off of everybody's plate until it makes itself sick. And a sick lithium battery is likely to burst into flames. So you need to tell it when it's full, and you need to cut it off as soon as it is. The way you do that is by setting up a battery management system, or BMS. 057 sells what they call a mini BMS that's compatible with these modules. What it does is senses the battery voltage and temperature, and it allows you to program set points where you want some external action to occur. For example, if the battery voltage is too high, you want to shut off the charging source. Equipment in this system is designed to work well with lead-acid batteries. The solar charge controller manages reasonably well with the lithium charge profile, but the inverter charger is stretched past its low voltage limit. The Tesla batteries operate at 24 volts, and the old lead-acid batteries are also 24 volts, but the voltage range between them is quite different. The Teslas operate between about 16 and 25 volts, and a 24-volt lead-acid system operates between about 23 and 30 volts. So all of the charging parameters needed to be reset throughout the system. This became a problem for the inverter when using a generator to charge the batteries instead of solar. The lowest voltage setting on the inverter-based charger is higher than what the batteries want to see. This means that an external control is required to turn off the charger. Fortunately, that can be handled through the BMS. Even though the charge controllers have the correct settings, I can't be sure that somebody won't someday go in and change a setting, or that a controller might fail in a particularly bad way. I set up the BMS to control all the charging and loads based on the battery voltage and temperature. If the batteries get too hot or too cold, or the voltage gets too high or too low, you end up with that bad dog at the party. So here's how the BMS works. Inside, there's a relay that sends a signal to whatever outboard control system you design. In this case, I used the output signal of the BMS to switch an external relay that has two functions. The most important function is to send a signal to the circuit breaker to turn off the charging source or the DC loads. The other function is to turn the appropriate green light to red on the LED monitor, signaling an event that requires attention. I used shunt trip breakers that open when a voltage signal is received. There are 4 of these breakers, one for the solar DC charging, one for the generator AC charging input, and one each for DC power input to the 2 inverters. These are all what I'd consider redundant fail-safe system except for the generator charging breaker. Because I can't set the inverter to a low enough voltage for the batteries, the BMS is set to open the AC charging input breaker when the batteries achieve their charged set point. The shunt trip breakers only need a brief voltage pulse to activate and open. The coils will burn up if you leave the power connected to them for more than about 15 seconds. This required installing a simple resistor capacitor network as a timer for each of the shunt coils. I know there's going to be some questions on how the control circuit works and how it gets wired together. So I'm going to start with a simple schematic with our basic building blocks. We've got the battery, the BMS, a power breaker. This is one of the big DC breakers with the shunt trip on it. Shunt trip is actually a coil, a relay coil inside. And there's going to be another relay. Okay, so this is our basic system layout. So the first thing is we come out of the battery with a main fuse. In this case, it's a 4 amp fuse. This is a 1/4 amp fuse that protects the BMS relays. After the 4 amp fuse, we're going to another fuse, and this will go to the relays. This is a 3 amp fuse. So this is our control circuit relay. The BMS is the sensor, and that has a very small low current relay inside of it. And those relays will activate based on the set points. So we've got power running everywhere that we need to. This 3 amp fuse ultimately protects the shunt coil. Now, just to simplify things, one side of everything goes to ground. Little jumper there. Okay, we've got all our grounds and our main power connected. Let's use an example of if the voltage gets too high, we want to shut off the power in. This is our main DC power in, and this would be our DC power out to the inverter, which gives our AC out. Okay, so under normal circumstances, everything is flowing as it should be. When this coil is activated, it trips the breaker and turns off the power. The way that coil gets activated is, again, through the BMS setting, and we have an output signal that goes to our control relay, activates the control relay, throws this closed, and sends 24 volts through that relay into the shunt trip coil, opening the breaker. Now remember, this coil only needs a momentary pulse to close. And if you leave voltage on it for too long, that coil will burn up. So the time delay circuit was hooked up in the ground, on the ground side. So let's ignore that for a moment. And we've got our resistor and our capacitor, and these are both tied to ground. I may have done this backwards. The electrolytic capacitor that I used, obviously the negative goes to the ground. 24 volt supply goes here. So the coil is activated when the BMS sends a signal. That closes the relay, energizing this coil, opening the breaker. We need the time delay circuit in here so we don't burn out the breaker. So what happens is this coil goes high, and we have a reference to ground on the other side until the capacitor is charged. And once that capacitor is charged, this coil is de-energized and the relay opens up. And it stays that way until the error condition is removed. So in this case, we have a 10 kilo ohm resistor and a 1000 microfarad capacitor. The math works out that this is about a 10-second delay. In reality, it's only about 2 seconds because of the nature of how the coil works and the charge and discharge characteristics of how this circuit bleeds itself off and when this coil is actually activated. So you may need to do some trial and error based on the equipment that you end up with. Okay, what about the LEDs? The LED circuit is fairly straightforward. I use a tricolor LED, and one side's grounded, green all is well. We're connected straight to power. And of course there's a dropping resistor in line here. When the BMS sends a signal to the coil that tells us something is not right, that same signal goes, you'll have to forgive my drawing, I am not an artist, again through a dropping resistor, and this goes to the red side. So when this goes high, the red overrides the green color and it glows bright red. One of the LEDs in the circuit is wired to glow red if this fuse blows. So that way we have an indication that the entire BMS has gone down, and we'll need to troubleshoot why that is. So this is a basic overall schematic of how that control system works. And each BMS has 2 triggers. So I've got 4 relays in that box. I only actually used 3 of them, but there's a 4th one in there in case I want to add another function. So each BMS control signal output would have an identical parallel circuit attached to it. And that's basically how it works. Overall, I'm happy with how this system works. The batteries deliver what they're rated to deliver. The mini BMS accurately does its job of balancing the cells and sending temperature and voltage signals to the outboard control system. Everything has a fuse, and if anything goes wrong, a red light on the monitor turns on. This is not lead acid. They are not forgiving. Set up the charge profile carefully. Follow the manufacturer's instructions. Research the specific lithium-ion battery technology you're using. There are a handful of lithium technologies out there, and they all are slightly different in terms of the charge profile and the temperatures at which they can operate. There's a reason that the Tesla Model S has an onboard heating and cooling system for the batteries and a fairly complex BMS system. Safety has to come first on these things. This project came along at just the right time to give me something to do during the COVID pandemic. So here's my gratuitous COVID hair shot. And here are the batteries in their new home. I hope this video was helpful, that you'll like it and subscribe to it, and maybe even buy the book. You will not be disappointed.